This section is on forced oscillations and resonance. We have to state what is meant by natural frequency of vibration and forced oscillations. Most bodies oscillate with a certain frequency, like a pendulum or a mass on a spring. When it is moved from its equilibrium position, it moves to and fro, up and down, or it moves back, and the system oscillates with a certain natural frequency. A pendulum is a very simple oscillator, and so is a mass on a spring. So, this is an example. The pendulum is pushed once, and it basically oscillates around the equilibrium position. If you have a car suspension and the car bumps over a speed bump, the car will bounce up and down a little bit and it will oscillate around the equilibrium position. When you tap a tuning fork, it will vibrate, and at a frequency, which is the frequency of the tuning fork, it will be its natural frequency. There are some systems which have many different possible modes of vibration with different frequencies. A forced oscillation. When there's a body B which exerts a periodical force on body A and causes it to oscillate at the frequency that the driving force oscillates. This driving force comes from another system. This is a forced oscillation. For example, if you are pushing the swing and you are pushing it at exactly the same frequency as the natural frequency of the swing, the amplitude would get bigger and bigger, and this will result in resonance. So the forced oscillation is basically when the driving frequency and the natural frequency of the oscillator are the same. You will get an amplitude which increases and you will get resonance. Here we have a graph which will show this. When the driving frequency equals the natural frequency of the oscillator, in other words F is equal to F0, F0 is the natural frequency, you will get an increased amplitude. The amplitude will depend on how damped the system is. But let's take the red line here. The natural frequency is F0. If the frequency is a little bit less than F0, it will reach a certain amplitude here. As it approaches F0, when it equals F0, you will get resonance, and the amplitude increases until this point here. It won't increase to be more than that because it's heavily damped. It will be losing a lot of energy to the surroundings. If we take an example of a spring or swing or whatever, which is lightly damped, the amplitude is going to be even greater. If it's undamped, the amplitude will be so great it will often result in the destruction of the oscillator. So the graph is very steep with a large amplitude if there is no or little damping, and the driving frequency is almost or equal to the natural frequency of the oscillator. So what is meant by resonance? The resonance is when the driving frequency is the same as the natural frequency. Each oscillation is driven to a larger amplitude by the driving frequency, and the amplitude, which is a maximum, which is limited by how damped the oscillator is. An example would be walking across a footbridge. Soldiers are expected to break step when they walk across a footbridge, because if their marching equals the natural frequency of the bridge will start to oscillate from side to side, the amplitude would increase until the bridge gets destroyed. Also, in an electronic circuit, you can get resonance. We have an input frequency to the current. If it's equal to the natural frequency of the circuit, then the amplitude will get bigger and then you get resonance. Here we can demonstrate resonance using this Java program. Here we have a weight which is on a spring. Here we have a driving force. So this will move up and down and will cause some motion in the spring at the bottom, and the mass will oscillate. Now notice that the frequency of this one is very slow, and the natural frequency of this is a bit bigger. Let's look at this graph. The vertical axis is the amplitude of the swing. Horizontally, we basically have the frequency of the driving force. Marked here, W0, this is basically angular frequency of the oscillator, the blue oscillator. The driving force is has a smaller frequency than the oscillator, so the amplitude is not very great. So we'll reset, start with 2.10. Start. Now the frequency is a bit higher, and it's getting close to the natural frequency of the oscillator. Notice that the amplitude of oscillation is much bigger this time. So you can see here vertically the amplitude is somewhat bigger. Try one more. Let's try 3.1, and we'll start this. Start. Notice here that the frequency of the driving force is pretty much the same as the frequency of the oscillator, and this is resonance. The amplitude gets so great that this spring is going to fail because it gets pushed so much that it pushes into itself, let's say. So the driving frequency is equal to the frequency of the oscillator, and then you'll get resonance. The amplitude, it gets so great that you will get some damage. What we could do, however, we could reduce it by increasing the attenuation, which is basically the amount of damping. Let's have this to 0.8 and start again. Notice that we still have the resonant frequency, but the amplitude is really quite small because the damping is so great.